So within anaerobic metabolism, we have to worry about our initial metabolite and our terminal metabolite. That is, what's going to happen in terms of glucose and pyruvate as it allows for anaerobic metabolism to be used and continue. And so let's start off by taking a look at what's referred to as the fates of pyruvate. And so the fates of pyruvate are going to determine based off of the need for ATP, in which we have two distinct fates that can take place based off of the immediate need for ATP reproduction. If there is oxygen available and enough oxygen available for the cell, it's going to move towards the Krebs cycle. However, if we don't have enough oxygen available for the cell, we're going to move towards lactate and NAD metabolism. Now, at all times within the cell, we are going to be going in both directions here with pyruvate. We're going to be going towards the Krebs cycle and we're going to be going towards lactate metabolism. The direction that it goes is going to be based off of the intensity of demand. That is, what is the overall demand for ATP that is there? And do I have enough oxygen available to allow for aerobic metabolism to take place, or do I have to continue with the anaerobic metabolism? This typically leads to a phenomenon known as oxygen debt. This is related to the triphasic response within respiratory functions, which we usually refer to as excessive post-exertional oxygen consumption, or EPOC. And what we're attempting to do is attempting to supply enough oxygen to go about and allow for lactate to be oxidized back to pyruvate to go about doing other metabolic processes. Now, what we have to remember here is that this does not cause the burning sensations that we associate with high intensity exercise, nor is it the sole reason for fatigue to take place with high intensity, short duration exercise. So we start with the formation of pyruvate. Pyruvate has one of two options it can take. It can be transported into the mitochondria when we have oxygen available. It undergoes a acetylation reaction. This acetylation reaction is going to form acetyl-CoA, and the acetyl-CoA is what is actually going to be entering into the Krebs cycle. This is the first spot where we need oxygen available because oxygen is going to be used with the pyruvate dehydrogenase reaction, forming the first molecule of CO2 that we associate with cellular respiration. If, on the other hand, we still need ATP, but we don't have enough oxygen available, or we want to propagate the continuation of glycolysis, we have to get NADs back. And so what ends up happening is that lactate dehydrogenase is going to go about reducing pyruvate into lactate, allowing for the regeneration of NAD to go back into glycolysis. We have the rate limiting step here, which is the amount of pyruvate being formed and the level of oxygen available to the cell. And so we have two key enzymes coming into play here: LDH, lactate dehydrogenase, and PDH, pyruvate dehydrogenase. Now, this is what happens if we need ATP. However, if we are copacetic with our ATP levels, we can go about using our pyruvate and as well as our lactate in anabolic reactions. This includes the formation of amino acids. In neurotransmitters, this will lead to, neurons, this will lead to the formation of neurotransmitters. In certain cells of the body, in particular the hepatocytes, and to a lesser extent the juxtarenal cells or the juxtaglomerular cells and the juxtanephronic cells of the renals of the kidneys, we will undergo a process known as gluconeogenesis, in which the pyruvate and the lactate that's in circulation will undergo reactions to go about producing glucose. And we'll give a little bit more detail into that here in a second when we look at glucose itself. So let's throw all of this anaerobic metabolism together to see what we can get from the anaerobic metabolism. So when we look at anaerobic metabolism, remember we're going to start with the phosphagen pathways, so the ATP-CP cycle. We get a few seconds worth of ATP return to the cells for exertion. We will then move into glycolysis, where we will go ahead and take our glucose and form it into pyruvate, allowing for the formation of NADH, H+, and ATP to come out as byproducts. Pyruvate will then interact with lactate dehydrogenase to form lactate, reforming NADs, which will then go back into glycolysis. So what we're doing here is we're cycling in order to ensure that we can have continuation of glycolysis. This gives us ATP regenerations for short durations, all by itself, or for when we have a high amount of ATP demands. The lactate that's being produced as it starts to accumulate within the cell will go about exocytotically releasing it. And once again, what to remember is that this cycle does not cause the burning, and this cycle does not cause the fatigue that we normally associate with the high intensity exercises. And we'll get more into that when we talk about what actually causes fatigue when we look at muscle contractions. So that deals with pyruvate, that deals with the overall anaerobic pathway. But we also have to look at where do we get the initial fuel source for this anaerobic pathway outside of the ATP-CP. And so when we look at glucose metabolism, we look at glucose regulation, it's both hormonally and metabolically regulated. Hormones of importance include insulin, glucagon, irisin, IL-1, IL-6, IL-10, epinephrine, leptin, adiponectin, testosterone, and cortisol, just to name a few. Metabolically, it will be regulated, and enzymatically, we will have regulations by adenosine, AMPK, ATP, and then regulations on the pathways that regulate mTOR, the AKT, the ERK1, ERK2 pathway, and the FOXO1 pathway. All of these pathways are going to be regulating which direction we are going to be putting glucose into glucose metabolism. And so when we look at glucose metabolism, we have one of three ways that we can do it. We can either go glycolysis, or we can go glycogenesis, making glycogen, or we can go ahead and break down glycogen, glycogenolysis. At hepatocytes, we have another pathway that can come into play, and that is the gluconeogenesis pathway. And we'll take a look at that in a second here. So let's take a look at the glycogenesis versus the glycolysis. And this is all going to be based off of, am I stimulating one enzyme or another? If I stimulate hexokinase, we're going to form glucose 6-phosphate, which will go ahead and enter into glycolysis. However, if we come about and instead of stimulating hexokinase, we stimulate glucokinase, we still get that first spot. We still get that glucose 6-phosphate being developed, but we also stimulate other enzymes that come into play, where instead of forming fructose 6-phosphate, we form glucose 1-phosphate. This glucose 1-phosphate undergoes what's referred to as a uridanol reaction, forming uridine diphosphate glucose. This will then link up with other uridanol units, forming glycogen. And so glycogen is this big long chain of glucose molecules held together by what's referred to as the alpha bonding units. And we'll talk more about alpha and beta bonding units when we talk about digestion of carbohydrates. So the other way of looking at what's going on is what happens if we have glycogen, but we need to get back to glucose. And so once again, we have all of the intermediates, but now we're going to be changing where we're going. And so we start off with glycogen. Glycogen is going to interact with what's referred to as phosphorylase, and this is going to split one of the terminal glucoses off of the glycogen at one of the alpha bonds by sticking a phosphate onto it, forming glucose 1-phosphate. Glucose 1-phosphate will then form glucose 6-phosphate. Glucose 6-phosphate will then go about undergoing a secondary reaction with a phosphatase enzyme, splitting off the phosphate, forming glucose. That phosphate that gets freed up will then interact with the phosphorylase, splitting another glucose away from the glycogen, and the cycle will continue. Now notice, The glycogenolysis pathway is going to be under regulation of glucagon and epinephrine, whereas the the glycogenesis pathway is under insulin regulation. Glycolysis will be slowed down with high levels of insulin and will be truncated, almost stopped, with high levels of glucagon and epinephrine. So how can we go about making sure that we have constant amounts of glucose? So we need glucose in order to do anaerobic metabolism. We need glucose in order to do aerobic metabolism. But we don't have to be constantly consuming glucose. We have to have a stable level of glucose, but we need to make sure that we have glucose available to us without having to constantly be consuming glucose. And this is where we are going to be dealing with what's referred to as the Cori cycle. And so the Cori cycle is the homeostatic regulation of glucose based off of the balance between glucose utilization, the formation of pyruvate and lactate, and the production of glucose from the liver via gluconeogenesis. And so if we look at the Cori cycle, what ends up happening is we start to produce lactate and pyruvate that gets released from the cell. This gets transported to the liver where it undergoes a chemical reaction where lactate and pyruvate will be combined in order to form glucose. And then that glucose is then going to be released to go back to be used at the peripheral tissues. Now, this Cori cycle will start to get modulated and modified based off of other hormonal signals in what is usually referred to as neogenic glucose sparing shift. This is where we hormonally will shift the fuel utilization at tissues away from carbohydrates, away from glucose and fructose, and towards the other fuel sources, lipids and amino acids. The typical signals are going to be based off of inflammatory regulators, glucagon and cortisol. And so the first signal here is where we get glucagon coming in and stimulating the release of glucose from glycogen. Now, most of this will be used at the peripheral tissues. However, when we have inflammation happen at the same time, this glucose will go about being released into circulation to go to tissues that are glucose obligated tissues, immune tissue, neurons. At the same time, if we happen to have the inflammatory responses, we're going to get cortisol coming in. Cortisol is going to stimulate the breakdown of proteins, in particular collagen proteins, to release amino acids. Some of those amino acids, alanine, glutamine, will be released to head towards the liver. Other amino acids will undergo a deamination process within the peripheral tissues, where we'll produce carbohydrates that can go about being used within Krebs cycle. Additionally, we'll get testosterone, epinephrine, and small molecular weight growth hormones, which will all stimulate the breakdown of lipid droplets, in which the glycerol molecules that get formed will get released into circulation and head to the liver. The fatty acids will undergo a movement into the mitochondria where they will undergo beta oxidation to allow for the formation of acetyl-CoAs, to allow for aerobic metabolism to take place. All of the amino acids that go into circulation, glycerol that goes into circulation, will get taken up into the liver and will undergo a process where they will get modified into glucose metabolites to undergo the process of gluconeogenesis. At the same time, glucagon and epinephrine will stimulate the release of glucose from glycogen stores. All of this glucose will go into circulation. The glucose that goes into circulation under these conditions do not get taken in at peripheral tissues unless they are glucose obligated tissues. This pathway here is done to ensure that the glucose obligated tissues, immune cells and neurons, have enough glucose in order to maintain their function. So let's take a look at this gluconeogenic pathway and let's review the glycogenesis and glycolysis pathways. So glycogenesis and glycogenolysis. Glycogenesis, we take glucose via glucokinase and go about forming glycogen. Glycogenolysis, we take glycogen, we react it with phosphorylase, forming glucose 1-phosphate. Glucose 1-phosphate gets converted to glucose 6-phosphate, interacts with phosphatase to form glucose. Now, gluconeogenesis, if you were to go by what the textbook tells you, is the production of glucose from non-carbohydrate sources. The problem is that we don't have the enzymes to fix carbon, which means that we have to come from a carbohydrate source. The carbohydrate source here is either pyruvate or lactate. To a lesser extent, we will get glycerol. All of those are carbohydrates. More importantly, they are glucose metabolites. Gluconeogenesis is the production of glucose from glucose metabolites. This is only going to occur in the hepatocytes and to a lesser extent, the juxtaglomerular and juxtanephronic cells within the kidneys, in which lactate undergoes a carboxylation to form pyruvate. Pyruvate will get modified into glycerol 3-phosphate, which gets modified to glucose 6-phosphate, which undergoes a reaction with phosphatase to form glucose. Now, this is where lactate and pyruvate are going to come into play, but that's only part of it. We can also get pyruvate from other sources. We can go about doing deamination of the glucogenic amino acids. This produces the pyruvate that can then get used in the gluconeogenic pathway. In particular for hepatocytes, alanine and glutamine. We can take the glycerol that is coming from lipolysis and we can insert it via an aldolation and phosphorylation reaction to form glyceraldehyde 3-phosphate. But we have to utilize glucose metabolites in order to allow for gluconeogenesis. The process of gluconeogenesis, the process of glycogenolysis, ensures that glucose levels will be maintained at homeostatic levels throughout the body. These pathways ensure that we have enough glucose available to match the 120 grams of glucose that is necessary for normal neural functions. These pathways will increase rates of activity with inflammation.